Okay, we're going to take a look at problem 634 from our application problems for module 6. This is coming out of the handout that we have for chapter 6 here, not out of our textbook. And it is on page 127. So I have it underneath my camera right now. So this is going to be the frame that we're going to be looking at. And as we can see here, before we kind of get started and devise, we have a continuous member going from from C through B down to A. This is going to be a reaction at a pin support. The other member that we have is going to start at B, going to go through and all the way down to D, which is also going to be another reaction as a pin support. So just like truss problems, when we look at frames, we are going to keep it all together and we're going to try to find the reactions at the supports. In this case, we have a pin support at A and a pin support at D, okay? In this case, I'm going to tell you, we're probably not going to be able to solve for all of them, but as we know, that's okay. We can start going into the members then, all right? So first things first, we're going to start by drawing a free body diagram of the entire frame together, and we're going to focus on trying to find the reactions at our supports, okay? So I am going to do that on the side here. So this is problem 634. I'm going to put my convention in my upper right-hand corner here. All right. And as we were working on 4 frame problems, we have to know which, members are continuous. So I do give frame problems a little bit of thickness when I want to see that my member, goes through a joint, for instance. So you're going to notice I add thickness here because that member CBA is a continuous member. And down here at A is going to be my pin support. So I'm going to call that A. Just going to kind of look here. C is the very top, and we have a force of 1,000 pounds. So that's going to be, 2,000 pounds. And then we've got a pin connection at B. So I'm just going to show that and that's an internal pin. Okay. Internal pin connection at B. And then we've got another even here. This is going to be 250. So shorter, 250 pounds. Right there. So this is 3 feet. This is 3 feet. And then it's 6 feet down to A. Okay, where we have a pin connection, so or a pin reaction. So I'm going to put A a little bit higher here. Since this is a reaction at a pin, I'm just going to show the X and the Y lines for right now. So this is going to be an AX, this is going to be an AY, and I'll add the arrowheads after I kind of get other things in place. Okay, so that's my first member. Now, again, this is the first free body diagram that we're doing in order to show the frame all together, and we're solving for the reactions at the supports. Then I'm going to go over to D. So again, showing that there's a little bit of thickness here, that it's a continuous member. I'm going to show it kind of like that. And then this is going to be point D. That about halfway through here. We've got 500 pounds. And I see that that is going to be $4 feet. And then at D, we also have a pin reaction. So there's going to be an X and a Y at D here. Make my AY a little bit longer. And then this is also, it's in the middle, it's 4 feet between each point. Mine didn't come out exactly even, but the dimensions show that it's even. And then this is going to be DY. and this is gonna be dx. And as I'm looking, I'm just gonna double check I've got all my points, my dimensions for my overall free body diagram. So it looks like it's complete here. So I'll give you a little bit to catch up, and then we'll put our arrowheads, or go ahead and put your arrowheads on what you believe the directions of the reactions of the supports should be. Okay. And remember, we don't want to get too hung up in, are they in the right direction or not? They don't have to be correct, because our final answer will always let us know, did we assume the correct direction? And if we didn't, we just change it. No biggie. But we have to have forces there, recognize them. And because there's a pin reactions at each here, there'll be an X and a Y at both A and D. Now, as I look here, and again, this is me talking mine through. I don't know the directions off the top of my head, okay? So, so as I'm looking here, I'm noticing I have two forces that are applied that are going to the left in the X direction. So I'm just gonna show AX and DX going to the right. I don't know, we'll find out if I'm right or wrong. And like I said, our math will tell us if we're right or wrong. And then in terms of my Y directions, I see that I have the 500 going down. So I'm just gonna assume my AY going up and my DY going up. Okay, for only that reason. Again, we'll find out if we're correct or not. But I have to show two forces at both places because there's two pin reactions, two pin supports. All right, so now that I have my free body diagram done, I can now solve for the reactions at the supports. Okay, so reactions at supports. That's going to be my AX, my AY, my DX, my DY. Okay, so I have my three equations of equilibrium. So if I sum my forces in the X direction, I'm going to have two unknowns, right? So I'm going to kind of save that one. If I sum my forces in the Y direction, two unknowns. But I do have my sum of my moments, right, that I can use. So let's try to sum our moments around either A or D. Where do we want to sum around? Tell me. We'll do A. Yep. It's my favorite. Start on the left-hand side. So we're going to sum our moments around point A equal to 0 because we are in equilibrium. So now we're going to put our finger on A, and we're going to work around, and whatever forces cause our offset that cause rotation, we're going to include here. I'm going to start up here at my 250. So 250 pounds does cause rotation. Perpendicular distance is 6 feet, and it is going to go in a counterclockwise direction, which is positive according to my convention. So we're going to say 250 pounds times 6 feet, positive out front. Then I'm going to go to my next force. Finger on A, 2000. It's also going to rotate in a counterclockwise direction, positive, and its perpendicular distance is going to be 6 plus 6. So that's going to be 12 feet. So 2,000 pounds times 12 feet and positive out front counterclockwise direction. And then the next force causing rotation is going to be my 500, not the last, 500. Okay. So we're going to have 500 pounds times perpendicular distance of 4 feet. And it is going to rotate clockwise, which is negative out front. And now my last force causing rotation is my dy. Okay. So dy times 8 feet perpendicular distance. And it is going to rotate positive based on the direction that I have it. And those are all the forces causing rotation because dx and ax go right through the point. They don't cause rotation. So we set this equal to 0. Remember, equation of equilibrium has to have two sides. The left side is going to be my summing my moments, and I set that equal to 0. So now I just want to look, do I have one unknown? Yes. So I can go ahead and I can combine all these and solve for dy. So go ahead and do that. Go ahead and do that. I don't have my calculator today. I don't know where it is. Thought I had it in my bag, and when I looked, it wasn't there. Oh, this is 250, 250. Let's put the counts in there. Just want to double check the number really quickly. 37, okay. Now, as I find my dy, I ended up with a negative value, right, that I couldn't clear. So that means that I did not assume the correct direction. You may have, and that's okay. So I assumed it going up. It means that it's not going up. It's actually going down. Okay, so this is the actual direction going down of dy. So change it there and then make this positive. Okay. And your value should be 2937.5 for the magnitude. So I'm going to put that here, 2937.5 pounds. Okay, now that I know my dy, I can go ahead and solve for my ay. Okay, solve for my ay. So I'm going to sum my forces in the y direction equal to 0. Ay minus 500 pounds minus 2937.5 pounds is equal to 0. So combining those two and putting them to the other side, my ay will be so you should get 3437.5 pounds. Just taking a quick peek. Yep. And positive value means that we assumed the correct direction for this one. Okay. Now, we know these two, but the X's are going to have to stay where they're at. Okay, so there's going to end up being two unknowns here. We will find those as we do the members separately, and then we can bring them back. Okay, so we're gonna stop here on the full together free body diagram. And what we're now going to do is work on what is the reaction at that internal pin, which should help us figure out our dx and or our ax. So now we need to decide which member we're gonna look at, and I'm gonna suggest the vertical member. Then we don't have to worry about things at angles, okay? So vertical member here, we're gonna show member A, B, C. And we are going to show the applied loads, the reaction at the support, and we're gonna show AX here because there's gonna be a value. We may be able to calculate it at this point, okay? And then at B, this is an internal pin. So again, an X and a Y there as well. So I'm going to, on my next page here, draw the free body diagram of member A, B, C. Member A, B, C. So I'm gonna make mine a little bit larger because again, I want to make sure I get my labels on here. And I want to be sure that be able to see everything. So I'm going to start with my external loads here at A. I know I have that AX and that AY. Okay. The AY I know to be 37.5 pounds, and I know it's going up, so it stays in its exact same location. This is point A. AX, I assumed going to the right originally, so I'm going to keep it in that same orientation. Again, a reaction at a support is an external load or an applied load in that same class. So we want to make sure that we put it in the same direction. The other applied load that I have is up at the top here at C. I've got 2,000 pounds. And then a little bit lower here, about halfway, isn't it? I've got 250 pounds. And this is 6 feet here. Now B comes in right here, right between C and that 250. Okay, so 3 feet here, 3 feet here, and this is point B. Internal pin. So because it's a pin, just like a pin support, I'm gonna have an X and a Y. Okay, an X and a Y. I'm gonna have a BX and I'm gonna have a BY. So I like that. All right, now arrows on BX and BY. My Y, you'll notice that I only have one other Y unknown, or one other Y directed force, which is known, which is my AY. My AY is going up here, so that means my BY has to go down. It has to go down. And we can probably already assume what we know that number is going to be, but we'll show it in the sum of the forces in the Y equation in a little bit. My X at B, it's kind of hard to tell. I've got the AX down here that I assume going to the right. I've got 2 of them going to the left. Might as well show BX going to the right as well. We'll find out if we're correct or not. So now we're going to simply do our equations of equilibrium. Okay. So I'm going to start out by doing my Y's. Okay. Sum the forces in the Y because I can see that BY is my only unknown. So I'm going to have a negative BY plus 37.5 pounds. That was my AY equal to 0. Moving that to the other side, I'm going to have a negative BY is equal to a negative 37.5 pounds. They both become positive. So we assumed the correct direction at BY, which we were pretty sure. So BY is 37.5 pounds. Okay. This is one of our answers for our problem because we need to know what is the reaction of this internal pin. Okay. So this is the Y reaction at this internal pin. Now we've got 2 more unknowns here. We've got an AX and a BX. We sum our forces in the X direction right now. We're going to have 2 unknowns, right? So summing moments would make sense, okay? So I'm going to sum moments either around a B or an A. Which one do we want to sum around, B or A? B or A? A, okay, let's sum around A. So go ahead and sum your moment around A to solve for BX. I just solved for BX. Now I'm gonna have a couple here. I'm gonna actually sum my moments down here so I can have a longer space. So as I look here, I've got 250 times 6 feet, positive out front. I've got 2,000 times 12 feet, positive out front. And then I've got my BX times 9 feet, negative out front, because it's going clockwise. And I set that equal to 0. So my only unknown here is my BX. So I can go ahead and I can combine these, put them to the other side and solve for BX. So for member BX, as it's shown, I ended up with a positive value. So that means the direction I assumed was correct. And I got a value of 2833, which is consistent with the answer key. So 2833 pounds. Any questions there at all? Here's my moment equation. And then solving for that BX by dividing by the 9 feet. So then, once we have our BX, we'll notice that our only unknown then is going to be our AX. So we can sum our forces in our X direction now to equal to 0. And solve for AX. So sum our forces in the X direction equal to 0. Include those applied loads. So don't forget about the negative 2,000, the positive 2833 at BX, minus 2,250. Going to the left, and then I have a positive AX direction assumed right now, equal to 0. So I'm gonna sum these together, and then we'll put it to the other side and solve for AX. Do you end up with a negative 583? Yeah. So no worries, right? Our magnitude is good. Our magnitude is good. It's just that we assumed the wrong direction. So we're gonna make it positive. We're gonna erase our arrow, if you did it the same way I did. And it needs to go to the left instead, okay? So we're gonna put a box around this. Now, AX was one of our reactions that are supports on our put together free body diagram, okay? So what we need to do is we need to go back and we're gonna fill this in now. Over on our original first free body diagram, we're gonna change the direction of AX here. We're gonna make it go to the left. And now we can say that this is 583 pounds, right? We know that one. Which means, what can we do here on this free body diagram? If we know what AX is, do you see how we can now solve for DX, right? Let's go ahead and do that. Might as well do it right here. And then that way, when we do our last member here, we'll be able to check for equilibrium. So sum our forces in the X direction equal to 0. I'm going to sneak it in at the bottom. So I've got we had to make sure that we include the 2000 and the 250, and these are just going to be in the X direction. So negative 2000 pounds, negative 250 pounds, negative 583 pounds, and a positive dx, right? That's our only positive X direction, right? Negative, 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 positive. Okay, so I know I'm gonna get rid of that underneath. I'm kind of small down here. Set that equal to 0. So that's my sum of my forces in the X on the left-hand side. And it looks like we've assumed the correct direction for dx, but now we just got to add these all together. So dx is going to be equal to, these will be negative on this side. I'm going to put them to the other side. They become positive. So 2833 pounds. Okay. And just going to peek really quick. Yep. Correct answer. Okay. Now we're not done. We have to check for equilibrium on our final member. So I'm just going to write this up here, 2833 pounds. So what we need to do is we need to draw our member, our last member, and then we're going to put our reactions at B, and we're going to put our reactions at D, and we're going to put the 500, and we're going to make sure that everything equals 0. Now, remember, when I have an internal pin like this, when I have it all together as a free body diagram, we don't include it in our forces, because what's happening is they're like reacting on each other internally, okay? And they're in equilibrium. So what we do is, once we know their magnitude on one member and we know their direction, which we know both BX and BY on this member, now when we go to the other member, BD, we are going to use the same magnitude, but we're going to switch the directions opposite. So that way B on the next member is going to be going to the left, BX is going to be going to the left, BY is going to be going up. Okay. So go ahead and draw the free body diagram of BD with the 500, with the reactions that stay the same direction at DX and DY, but then the BX, BY, because it's an internal pin, those change direction. I'll do it on the side here as well. Number BD. I know a point of sometimes confusion for students is when do they show the X's and the Y's and when they don't? B is an internal pin to the structure. So it is considered one that we would change the directions when we look member to member. D is a pin reaction, a support for the entire structure. So because it's a reaction at the support, it's like an applied load. It does not change direction. So we keep those in their same orientation that we calculated when we had the full free body diagram together. Applied loads remain the same. It's just internal pins. Those are the ones that are going to change direction from one member to the other. Same magnitude, just opposite direction. So as we look back at B, when we calculated it on A, B, C, again, we showed it going to the right, or we confirmed it going to the right on this member at 2833, and we confirmed BY going down 3437.5. So now on this member, up for that BY 3437.5, and to the left for the X 2833. The 500 still goes down. And then we determine that DY at our full together frame to be going down 2937.5. And then we just calculated our DX because we found out our AX to be 2833 going to the right. These stay in the same direction. Okay. Now we're going to sum our forces in the X and Y, and we're going to hope for the best. Okay. I think we're in good shape. So I want you to still do this. Sum the forces in the X equals 0. Even though we know everything here, there's nothing to solve for. You're proving equilibrium. Okay. So sum your forces in the X here. We've got a negative 2833 pounds, right? Up here at B. And then our other X is down here at D, a plus 2833 pounds equal to 0. Sure enough, 0 equals 0. So it's like, check. Good job. And now we're going to do the same thing in the Y. Sum the forces in the Y equals 0. Again, you have to do this. I know you might be like, I can see it's good. No, show me, show me. 37.5 pounds going up, minus 500 going down, minus 37.5 pounds going down is equal to 0. These two, right, combined, this is going to be a negative 37.5. So indeed, 0 equals 0. And that is good. And if you want to show a smiley face, I totally get it. It's a long problem to get to the end and be like, yes, it worked out. And it did. It worked out. Then we know that we did everything correct. Unfortunately, we don't have an MD solids to help us with this one. So it is getting to the end or checking your answers as you go along. There are some intermittently as you go that you can check to be sure you're on the right track as well. All right, 634. Any questions on that one? Okay. Yep, you do have a frame problem that you'll be doing for your unit assessment. So it's good. It's good practice. I am going to stop the recording then.